Now we are working with implicit differentiation. So far we've been working with functions such as like y's explicit equations, like y is equal to x plus 16, or f of x is equal to x plus 16. It's explicit. Y is equal to something. We're going to start working with implicit equations. So for example, if you have an equation right here, x squared plus y squared is equal to 16. Like this is the area, no, this graphs out to be a circle. But it's implicit, it's not explicit. There's an x squared and y squared. They don't tell you directly, like, oh, y is equal to something. They give it to you like this. So far we've been doing all of our derivatives in terms of x, right? The derivative of x is just 1. Technically, it's a dx over dx, which is equal to 1. The derivative of x squared is 2x dx, because they're differentiating with respect to x over the dx. And well, it's just 2x, right? And then right here, derivative of e to the 5x is 5e to the 5x times dx, which is just 5e to the 5x. We never write it, the dx over dx normally, because like we don't need to. But here, if you take the derivative with respect to x of y, it's not 1, it's just dy dx. If you take the derivative of y squared, you can pretend this was like an x, so it'll just be a 2y using the power rule, but then you got to write a dy dx. And then it doesn't simplify out like it does over here because they're different variables. And then over here it will just be 5e to the 5y times dy dx. Right here, here's an example we'll work on. Find dy dx for y squared minus 5x cubed equals 3y. First step you want to do is take the derivative. Each time the derivative of y is involved, just include a dy dx. So the derivative of y squared is, well, just 2y, but because it's a y and you're taking the derivative with respect to x, write a dy dx. And then we subtract, well, this is an x, so we do it as normal. 15x squared equals 3 dy dx. Gather all terms with dy dx on the left side, everything else on the right. So this is similar to like algebra 2, algebra 1, when you're solving for isolating a variable. You're doing the same thing here, but you're just isolating the dy dx's and getting everything else on the other side. So we can leave the 2y dy dx here, subtract this over, minus 3 dy dx, bring the negative 15x squared over, that becomes a positive 15x squared. And now we can factor out the dy dx. Well, since there's two terms, if there's only one dy dx, you don't need to factor it out. But it's dy dx, factor that out, you're left with 2y minus 3 equals 15x squared. And then to solve for dy dx, well, you just divide both sides by 2y minus 3. Dy dx is equal to 15x squared over 2y minus 3. And that is your answer right there for this example. All right, one key note here, instead of dy dx, you can also write y prime if you want, just to save some room. So right here, the derivative of y cubed, we could do it this way. 3y squared times y prime minus derivative of 2x, which is 2, equals derivative of x to the fourth is 4x cubed, and then plus 2 y prime. So now we're going to get all the dy dx's, or the y primes, on one side. Let's do the left. So leave the 3y squared y prime minus the 2y prime over, equals 4x cubed. And we're bringing the 2 over. Now we can factor out the y prime. Y prime, it'll become 3y squared minus 2 equals 4x cubed plus 2. So here you can say y prime or y prime is equal to 4x cubed plus 2 all over 3y squared minus 2. This next one here. This is trickier because you have to use the chain rule and then the product rule. The outer function's a sine, right? So cosine of xy as normal, but then you have to multiply by the derivative of the inside. And that's when you use the product rule. So you take the derivative of x, which is 1, leave the y, 1 times y plus, leave the x, find the derivative of y, which is y prime, equals the derivative of 10x, which is 10. So now, let's just divide both sides by cosine of xy. So we have, what I have here underlined is what we have on the left now. Y plus xy prime is equal to 10 over cosine of xy. And now what we can do is subtract the y over. So xy prime is equal to 10 over cosine of xy minus y. And then now we just divide this whole thing here by x. So y prime is equal to this whole thing here, 10 divided by cosine of xy minus y all over x. That's your final answer there. All right, let's go to the next page here. Find the equation of all tangent lines for x squared plus y squared equals 4 when x is equal to 1. So, find the equations of all tangent lines. So, if you remember the formula for a tangent line, it's going to be, let me make this size here, y minus y1 is equal to m times x minus x1. If you want to find the equation of a tangent line here, m is just going to be your dy dx or your y prime. So what we can do is implicitly differentiate this. 2x plus 2y prime, 2y times y prime equals 0. So then y prime, you subtract the 2x over and then divide by 2y. You end up getting a negative x over y. So here we have x is 1, right? So it's negative 1 over y, but we don't know what the y is. So we can actually plug in the 1 here to the original equation to get what y is equal to. If you do 1 squared plus y squared is equal to 4, y squared is equal to, well, 4 minus 1 is 3. And square root both sides, y is equal to plus or minus root 3. So y is either plus or minus root 3 and x is 1. So we have two slopes. The first slope here is going to be, looks like we have two tangent lines here because there's two different slopes. So we can say like the slope of one line is equal to negative 1 over positive root 3. And the slope of the other line we can say is, well, negative 1 over negative root 3, which is just a positive 1 over root 3. And now we can just write out our equations of our tangent lines. Y minus y1. We can say, so when our y value was positive root 3, well, what's y? So it's minus root 3. Our slope is negative 1 over root 3, x minus 1. That's the equation of one line, and we got one more we got to do. So when our y value was negative root 3, so y minus negative root 3 would be a y plus root 3 equal, we get a positive slope here. Be careful here. Times x minus 1. And that is our second equation for the tangent line. All right. Horizontal tangent lines exist when the slope dy dx is equal to 0. So this is where you have like either a flat line like this, right, where the slope is always 0, or maybe you have like a curve here, and you see like there's a horizontal tangent line right up here. But anywhere there's a horizontal tangent line. A vertical tangent line exists when the slope dy dx is undefined. Again, if there's this vertical straight and down line, like that's undefined. So that's a vertical tangent line. It could also be whenever the graph has like a cusp or a corner, such as this, and the derivative is undefined at a point. All right, find all horizontal tangent lines of the graph 3x squared plus 2y squared equals 16. So what we want to do is find when is dy dx equal to 0. I'm just going to use dy dx this time instead of y prime just to switch things up. So let's implicitly differentiate this first. 6x plus 4y times y prime, that's a y prime, equals 0. Oh, I said I would do dy dx, but you just did y prime instead, whatever. So 4y times y prime is equal to negative 6x. Y prime is equal to negative 6x over 4y. So that simplifies into negative 3x over 2y. So we have to take a look at this function right here. When is y prime equal to 0? So you can see y prime is equal to 0 whenever the top of this fraction is equal to 0. So that's when 3x is equal to 0, and then x is equal to 0. So again, we want to find a horizontal tangent line. A horizontal tangent line looks like this, right? It's going to be y is equal to something. So now that we have our x-coordinate, we have to find what the y is anytime it says horizontal. So we can plug that into our original equation right here. Plug the 0 in 3 times 0 squared plus 2y squared is equal to 16. That gets us 2y squared is equal to 16. Divide 2 on both sides, y squared is equal to 8. So then your horizontal tangent lines take the square root of both sides as y is equal to plus or minus square root of 8. So anytime it's y, it's a horizontal line here. So question 5, we're finding all vertical tangent lines, looking when y prime is undefined. So this is the same function as before. So we have the y prime is equal to negative 3x over 2y. We want to know, because it's vertical, when is dy dx undefined? That's when the bottom of the fraction's 0. So when is 2y equal to 0? Well, that's just when y is equal to 0. But now we have to find the x values. Sorry, because we're looking for a vertical graph, so that'd be a x. To represent that vertical line, it would be x equals something. And then we can just plug it into our original equation here. 3x squared plus 2 times 0 squared is equal to 16. 3x squared is equal to 16. X squared is equal to 16 over 3. And then x is just equal to plus or minus the square root of 16 over 3. And those are your two vertical tangent lines for this function here. You can go ahead and start the practice.